Okay, ladies and gentlemen, this is the last lesson that we're going to take a look at in our Unit 2 material for introduction or basic differentiation. And this lesson is going to kind of be a doozy. This is a very important lesson. This is going to be the kind of thing that the material that we're going to be introduced to here as far as what we're going to be looking at for position, velocity, and acceleration. This is going to follow us through most of this school year, okay? So it's a very important lesson. There's a lot of information to get through, so I'm going to try and get through it as quickly and efficiently as possible. But that being said, let's go ahead and get started on it. Here, what it's telling you in the lesson, we're going to be talking about how position, velocity, and acceleration are related to each other in context of a derivative. If you've taken a physics class, then the things that we're going to be looking at here ideally are going to be familiar to you. Here, this paragraph is kind of talking about really just the way the derivative is kind of how we annotate it or notate it in calculus. We've talked about using the prime notation where we just had the kind of the apostrophe to represent it, but what it's kind of looking at where I have it highlighted, because derivative essentially is a forgot the word for division for some reason for a second there, but it's essentially a division operation. So we always going to, so for the Leibniz notation that we're seeing, it's always going to be dy over dx to annotate the division of basic differentiation. Here, example 1, suppose that we have s equals s of t gives the distance in feet of an object from a fixed point in time after t seconds. So here, they're using that Leibniz notation to make sure that you understand what we're talking about. Here, ds over dt, time is almost always going to be the x-axis, and the s value, the ds portion, that's going to be its height or its position above or below something in feet in this case. So the derivative of the position function is going to be the velocity. So here, ds dt, that's going to be representing the velocity function. And a lot of times we'll just, we might say s of t for the position function, and understanding that the velocity is its derivative, we'll often just refer to that as v of t instead of ds dt. Here, describe the following notation. So ds dt, in this case, we're going to be looking at it, we're going to be identifying the velocity of something in terms of feet per second at 4 seconds. So here, this is the instantaneous rate of change. This is the velocity of something. The instantaneous rate of change would be the derivative of the position function in feet per second. Velocity is going to be synonymously used with speed. Although speed and velocity are pretty similar to each other, velocity may be negative to indicate a direction that it is going to be traveling. So here, what is the real world meaning of f prime of 4 is equal to 18? Well, here what we're talking about is we're saying that we're talking about 4 seconds. Okay, so at 4 seconds, the object has a velocity of 18 feet per second. And because it is positive, it's moving in a positive manner, meaning it's moving to the right or it's moving to up of a fixed point, typically the origin. Here, example 2, this particular example is not a serious heavy hitter in the things that we're talking about here, but Neil Armstrong stepped off the lunar module and picked up a moon rock from the surface of the moon. If he did, scientists say that the rock would have a velocity of 24 meters per second. The height of the moon rock can be modeled by the position function as it's given to you, 24t minus 0.8 t squared. So the negative 0.8 t squared, that would be the acceleration due to gravity on the moon in meters per second squared. So that's why it's going to be a little bit different than some of the position functions that you've seen previously, where it said like negative 16 t squared or negative 9.8 t squared for meters per second in for the acceleration due to gravity. So here the velocity, what I'm kind of illustrating with the text that's in blue is that the velocity function is the first derivative of the position function, and that the acceleration function is the second derivative of the position function. So in this case here, find the velocity and acceleration of the moon rock as a function of time. So for velocity, we need to take what is the velocity of the or we need to take the first derivative of the position function, which gives us the 24 minus 1.6 t. And the second thing it's asking us to do, it says find the acceleration function. Well, the acceleration function is going to be the derivative of the velocity function, so that's why we have an acceleration of negative 1.6. And I probably should have included, meters per second and meters per second squared for velocity and acceleration on that one, because they did give us units, but it's one of those things that, okay, well, good enough in hindsight, right? Here, example B, how long will it take for the rock to reach its maximum height? So here, the illustration that I have there on the right is Neil Armstrong up on the moon tossing a rock into the air. And anytime you throw anything into the air, it's going to have that parabolic motion to it. And what we're looking for is where the height reaches its maximum point, the velocity of the function is going to be 0 there, because it changes direction at that point. So where it changes from increasing to decreasing at the vertex of the parabola, then that's where the velocity of the function is going to be equal to 0. So I take the velocity function and I set it equal to 0, and then basically I'm going to solve for t here using just some basic algebra. So in this case, it would take 15 seconds for the rock to reach its maximum height, which is pretty impressive. I think if I threw something in the air and it took 15 seconds before it even got to its highest point, I'd feel pretty good about myself. How high did the rock go? So here we're looking for the overall height of the function. How high did it go up in the air? So we would be wanting to look at the position function, and I need the 15 seconds for time. So we know it took 15 seconds to reach its maximum height. So what is the maximum height? So 15 seconds after you throw it, using the position function, we'll say s of 15. And here, you may want to use a calculator to help you with the arithmetic here, but we're going to wind up with 180 meters, which is, again, sounds pretty impressive, 180 meters. Well, when did it hit the ground? When it hit the ground is, of course, the final solution of the position function, when time is going to be equal to, or when the height of the function is going to be equal to 0. So we're looking at the position function. We set it equal to 0 so to solve for time. Here I'm going to use the negative 0.8 as a greatest common factor, so that way I can set both of the functions, or both of the two factors, equal to 0. So the first solution that we get is that time is equal to 0. That's just before you throw the actual rock into the air. And it took 30 seconds for it to hit the ground, which makes sense because of the symmetrical nature of the parabola. If it took 15 seconds for it to reach its maximum, then it should take another 15 seconds for it to hit the ground. So 30 seconds sounds pretty reasonable. So here the time till the max height and the max height itself. Here what I'm explaining is, and I didn't put my exponent on the t squared. I didn't put that in the exponent spot, but it should be. This entire problem could have been solved without using any calculus, without finding the derivative of the position function. We could have easily taken some Algebra 2 concepts and put the function from standard form into vertex form, and then answered the question just as easily from there. So moving on, here in our last lesson, we defined y to be equal to s of t as a position function of some object. Okay, a lot of times we just refer to it as a particle. However, we can have that function to represent a whole lot of things, and they're giving some examples: the amount of rainfall over time, temperature of yams for some reason, volume of a cone, people infected by a virus. That seems pretty pertinent at the moment. And there's a whole lot of other situations that we could look at when we're talking about how rate of change can be applied to something in motion, and it doesn't have to actually be in what we think of as a straight line motion. It can be just in position in relation to a fixed point. Here, example 3, suppose we have function W, and that is going to be the daily quantity of water in gallons required for a palm tree of some height in feet. Explain the meaning of each expression. Now, if you want to try to answer these in advance, go ahead and pause the video and see if you can actually answer these and interpret the meaning of them. But here, where we just take the function W of 25 is going to be equal to 38, that's telling you that the height of the palm tree is 25 feet and that it's going to require 38 gallons of water every day, which, I don't know, seems like a lot to me, but I guess palm trees, that's how much they take. Maybe this isn't exactly accurate, I don't know. Maybe this is just a made-up example, but here, the inverse of W, where we're reversing the inputs and outputs, this is just saying that when the palm tree requires 38 gallons of water every day, its height is 25 feet. And part C, this is where we look at the derivative of the function. So here, W prime of 25, they're still telling you that the height is going to be 25 feet, but the amount of water that it's going to be needing is going to be increasing at a rate of 6 gallons per foot of height that it has. So now that we've had an opportunity to kind of look at, how derivatives are going to be applied and how we can interpret the meaning of them, let's take a look at an application problem. In this here, up at the top, it's illustrating the verbiage or the way people talk about rate of change. A lot of times people will simply say rate of change even though they're referring to the instantaneous or the derivative for the rate of change. So in this example C, or example 4, we have some function C of t represents the cost in dollars per day to air condition some Florida beach house where the temperature is going to be in degrees Fahrenheit. So here we have is, again, explain the meaning of the derivative. C prime of 90 is equal to 0.37. So again, I want you to pause the video and actually attempt to answer that in a complete sentence, and then hit play and see how your sentence and my sentences compare. So hopefully you've got your answer, and here's what I wrote, and to see if they kind of say the same thing. When the temperature is 90 degrees Fahrenheit, the air conditioning costs are increasing at a rate of 37 cents a day, which doesn't seem like a lot, but it can add up quite a bit, especially if you take into account, I probably wouldn't think of it in terms of a beach house because you may not be using your beach house every day, but think about how hot it is here in South Texas during the summer when we're dealing with triple degree temperatures and heat indexes of like 110, 113. Those air conditioning costs are going to skyrocket at that point. Here, example B, approximate the cost of the air conditioning for your beach house when the temperature is 94 degrees, given that at C of 90, if the temperature is at 90 degrees, it costs $2.64 to run your air conditioner for that day, And C prime of 90 shows you that it's increasing at a rate of 37 cents per day for every degree above 90 degrees. So here, 37 cents is going to be what we're looking at for our increase between 90 degrees and 94 degrees. So here I'm looking at it as a basic difference quotient, and that is going to allow us to substitute some values here. So again, we're looking for the cost at 94 degrees, so we're going to multiply by 4 and then add the 2.64, and so that tells you that the cost for 94 degree temperature is going to be $4.12 per day. And again, it may not seem like it's a lot, but think about July. July is 31 days. So real quick, what would that be? 412 times 31 days. That would be about $128 just for the air conditioner. And of course, you got your computer electronics going, your washer, your dryer, your water heater, your refrigerator, your all that stuff. And of course, 90 to 94 degrees, I think most of us would be happy with 94 degrees in July. I know I would, because boy, my utility bills are in the summer months. So moving on, now we're going to be taking a look at some vocabulary and how we're going to interpret the meaning of position, velocity, and acceleration. Here it's telling you we briefly define particle motion, and now we need to get some context with some vocabulary, some terminology that connects those three things in relation to motion. The function s of t gives the position function relative to an origin as some function over time. That's a position function. And here, consider an object is moving along a straight line. These objects move either horizontally or vertically. So horizontal or vertical motions, take a moment and think about things that could be horizontal or vertical. Here, horizontal motion, most things that you can use for locomotion, and vertical, basically anything that applies or that's subject to gravity could be used for vertical motion. So the function s of t or x of t is going to give the position of a function. A lot of times you'll see it as s of t, but sometimes you'll see it as x of t. As an object moves, its position changes over time, therefore the velocity can change over time. And the velocity is the derivative of the position function. So here we're going to be looking at terms of instantaneous velocity and how it's related to the position function. So instantaneous velocity tells how fast something is going at an exact instant and in which direction, because velocity can be positive or negative to indicate a direction that your particle is moving. So here the first derivative of the position function is the velocity function. That's why we say s prime of t is equal to v of t, and we could identify that by looking at the limit definition of the derivative, although we are definitely moving past that at this point. Here, how do we define the motion of an object? So if the velocity is greater than 0, that means we're moving something above the x-axis. If the velocity is greater than 0, we're going to be below the x-axis. Or if the velocity is 0, we are on the x-axis. So how does that look for horizontal and vertical motions? Well, if you're above the x-axis, that means you're either moving right, and if you're above the vertical line, it means you're moving up. So the converse of that, if you're below the x-axis, if your velocity is putting you in the negative portion of the bottom half of the graph, that means you're either going to move left or move down. Now, if your velocity is 0, that means you are stopped. If your velocity, your speed, your velocity is 0, you are not moving anywhere. So here, this is kind of what I was alluding to earlier at the bottom, where they're saying speed is represented as the absolute value of velocity. Velocity can be negative, indicating a direction that something is moving. So the absolute value of that number is what we would consider the speed of an object. Here, the acceleration, meaning that the acceleration is the second derivative of the position function or the first derivative of the velocity function. So how do we relate its motion for something on an x or on a normal plane next where in relation to the origin? Now here, what it's telling you, just because an object's acceleration is 0 does not mean that the object is stopped. And the analogy that they're giving you is about the cruise control on your car. You set the cruise control on your car at 65 miles an hour. That is your speed, that is your velocity, but you are not increasing or decreasing that, so the acceleration seems to be at 0. So while you're still moving, your velocity has some value to it. Because you're neither increasing nor decreasing that velocity, your acceleration is constant and remains the same, so it would be a horizontal line. So here, if the velocity is greater than 0, meaning that you have a positive slope for your velocity, that means you're going to be moving to the right or up, depending on your horizontal or vertical reference. If your acceleration is negative or less than 0, meaning that the velocity function would have a negative slope at that point, you would be moving left on the horizontal or down on the vertical. And if the acceleration is 0, then that means your velocity is constant, so it would be a horizontal line. So your velocity simply isn't changing. You're still moving, but the velocity is remaining a constant value. You're neither increasing your acceleration nor decreasing your acceleration. So here they're kind of talking about how you understand when you can interpret how your speed or how your acceleration is changing with relation to your velocity. If your velocity and acceleration have the same sign, so those first two rows, if the velocity and acceleration are positive, or if the velocity and acceleration are negative, both of those are going to indicate that they are increasing your speed. However, if the signs are opposite, meaning if your velocity is increasing but your acceleration is decreasing, or vice versa, that means that your overall speed of your object is going to slow down. So here we have a velocity function, and almost always when you're dealing with something related to position, velocity, acceleration, they're going to give you a velocity function. And we have a lot of questions associated with this velocity function graph. So let's just go ahead and get into them and see what we can interpret. Now again, I apologize in advance. This is going to be a little bit lengthy in terms of how we're interpreting it, but it is a very significant lesson, so please pay attention. Here, all of the questions that we're referring to are going to be referring to the same velocity function. Question 1, when is the particle moving at a constant speed? Meaning that the velocity is neither increasing or decreasing. It is a horizontal line. Well, that is on that very first line segment of the piecewise function that represents the velocity. It is between 0 and 1. When, and let me go ahead and move this out of the way. When is the particle moving to the right? Meaning that when is the velocity going to be greater than 0? And again, just looking at the graph, you can see it's going to be greater than 0 along the time from 0 to 2 seconds, or 0 to 2, because we don't actually know if it's in seconds here. When is the velocity, or when is the particle moving to the left? Meaning when is the velocity going to be below 0? Well, you can see that it's going to be below 0 from the time interval from 2 to 5 units, whatever those happen to be. Now, when is the particle speeding up? This is where we're looking at having the same sign for our velocity and our acceleration. Well, looking at the function itself from between 0 to 2, the velocity function is positive on the interval from 0 to 2. Now remember, acceleration is the derivative of the velocity, meaning that the slope of those lines represents the acceleration of the function. So from 0 to 1, the acceleration is constant, or is 0. You're neither increasing nor decreasing. From 1 to 2, the velocity is positive because it's above the x-axis, but the slope of that line means its acceleration is negative. Now, between 2 seconds and 3 seconds, or 2 to 3, I keep saying seconds, I'm not sure what the time interval is, but between 2 and 3, the velocity is negative, meaning it's below the x-axis. And the slope of that segment is also negative. So in that case, between 2 and 3 seconds, we have the same sign for the velocity and the acceleration. That means it is going to be speeding up at that point. So when is it slowing down? This is where we're looking to see velocity and acceleration having opposite signs. Well, we've already established that between 1 and 2, between time interval 1 and 2, the velocity is positive, but the acceleration is negative. So that is definitely one interval, but also between the interval between 3 and 5. The velocity function puts us below the x-axis at that point, or below the t-axis, if that's what you want to think of it as. But the slope of that line, the slope between 3 and 5, is increasing. So the acceleration, the derivative, the slope of the velocity is going to be positive. So it's going to be slowing down between 1 and 2 seconds and between 3 and 5. I keep saying seconds. I guess just accept that I'm going to keep saying it. But between 3 and 5 seconds. So when is the velocity increasing, meaning when is the acceleration going to be greater than 0? Well, the acceleration is greater than 0 anywhere we have a positive slope. And the only place where the acceleration has a positive slope is between the time interval of 3 to 5. When is the velocity decreasing, meaning when is the acceleration going to be less than 0? Well, there's two intervals where the acceleration is negative, it's less than 0. That's between 1 and 2 and between 2 and 3. And we do need to differentiate between the two because they clearly have different slopes. So looking at the next bit here, are your answers to questions 6 and 7 the same as your answers from 4 to 5? Now, on your notes, you probably need to go back and take a look at it. But here, what we're going to say is that, where did I have it? I guess I didn't type it up. So here, the acceleration and velocity, no, they're not going to have the same. And unfortunately, I apologize, I don't want to flip back and try and see what those were. But yeah, they're not going to be the same, and that has to do with, one, we're talking about velocity on one when the speed was increasing, meaning that the slope or the acceleration and velocity had the same signs, and here we're looking at seeing where your velocity is either increasing or decreasing based off of the slope of your the slope of its derivative, the slope of the acceleration function. And I don't know where that thing went. I thought I had it all typed up, but okay, well, moving on. 9, how fast is the particle moving at time is equal to 4 and in what direction? Well, here, come on, at 4, we're looking at the velocity. The velocity, when we think of how fast is something moving, we're thinking of the speed. So at 4, when you look at the function, that puts us about that -5. Okay, but remember the -5 is indicating the direction that it's moving, not how fast it's moving. Or when we think of speed, we take the absolute value of that. So here I would just say, how fast is it moving? It's moving at 5 units per element of time, whether they're seconds, minutes, hours, I don't know. What is the particle's velocity? Well, that's the same number, but now we're going to take the negative into account to indicate the direction that it's moving. 11, what is the average velocity? Now here, this is where things are going to start to get a little bit interesting. This is actually going to allude to what we're going to get to at some point, known as integration, the integral, the area under a curve. So here, what is the average velocity over the time interval from 2 to 3? So here, what we're looking at, the average velocity, meaning that horizontal line over the v that's representing the average velocity. It's the area bounded by the velocity curve along that time interval. So between 2 and 3, we have a triangle that has a base of 2 and a height of 10. So we're really looking for the area of that triangle between when time is 2 and when time is 10. So that's kind of how I'm looking at the area of my triangle. Now, of course, because we're moving down, the height of the triangle, meaning between the t-axis or the x-axis and the peak of the triangle goes down to a -10, we do need to make that value negative. So the average velocity in this case is going to be -5, and again, feet per second, inches per mile, I don't know. If we had units, we would include them there. When does the particle change direction? That indicates when the velocity is going to hit the x-intercept. So anytime it hits the x-intercept, that is going to indicate a change in direction. So here, when time is equal to 2, that's where it changes from either moving up to moving down or from moving right to moving left. How far does the particle move during the first second, and in which way? So here I didn't have it typed up, and apparently I had it saved, written out here. It's going to be moving 5 units to the right. So between the first second, that's that constant segment. So velocity is positive, so we're moving 5 units to the right, and that's because the value of the velocity is positive at that point. 14, again, how far to the right does the particle go, and when does it arrive there? So again, how far to the right, that's very similar to what we saw here in 11, where it's talking about the average velocity. Okay, how far does it go? We're talking about the overall movement or the displacement of something. How far did it move? That's going to refer to the area under the curve again. So in this case, we're looking at the area from 0 to 2. So you can think of it as kind of like a quadrilateral and a triangle where you're finding the areas of, or you can think of it as a trapezoid that you're finding the area of between 0 and 2. So anything that's above the x-axis, that's where it's moving to the right. So I want to find the area of that region from 0 to 2. So I can look at the area of the overall particle. At this case is going to be at 7.5 units. Okay, so moving on. What is the total distance that the particle traveled? Okay, so from when it started moving at 0 to when it stopped moving at time 5, yes, time 5, how far did it move? So again, very similar to what we just did a second ago, we're looking at the area that's going to be bounded by the velocity curve between the actual graph of the line segments that we see and the x or the t-axis, however you want to think of it. Well, we just found out that the movement to the right was, 7.5 units? So the area formed by the triangle between the horizontal t-axis and the 2 line segments has an area of 15 units. So the combination of the 7.5 motion, units of movement to the right plus the 15 units of movement to the left gives us overall 22.5 units. That's the actual distance that it traveled. Okay. Now the next one is talking about what's the particle's position after those 5 seconds. Well, the position in this case is going to be the difference between the motion to the right and to the left. This is what we would think of typically as a displacement. Okay, where is it so it might have moved a total of 22.5 units, but in relation to where it started, okay, this is where we take the difference between the left and right motion or the up and down motion. So it's negative 7.5 units to the left of where it started when it stops. What is the average velocity of the particle over the 5-second time interval? Well, here we're going to be looking at the average velocity. We're going to take the motion to the right, the 7.5, and the motion to the left, the 15, and we're going to really just take the average of that, just like what we normally do. The sum of the two, motions or the areas that we found divided by the total amount of time in this case gives us our velocity. There we go, of negative 1.5 units. And again, I keep saying seconds. I don't know that it's seconds, but. So are your answers to 15 and 16 the same? Well, look, we have them here. 15 is talking about the total distance, and 16 is referring to the displacement of where is the particle from its beginning point when it stops. And so no, they're not going to be the same. All right. Next, what is the average speed over this 5-second interval? So the average speed is just going to be your total distance divided by time. So your average speed is going to be 4.5 units per whatever unit of time, units of distance, units of length versus units of time. What is your particle's acceleration over the first second? Well, the acceleration, again, is going to be the slope of the velocity function. So at the beginning, 0 to 1, we have a horizontal line segment there. So the acceleration there is actually 0. Next, 21. Over what time intervals does the particle have positive acceleration? Well, this is where we're looking at having something where we're looking at the same signs of for velocity and acceleration. Over what intervals does a particle? Oh no, not that's. Pardon me, I misspoke. I'm not talking about same signs. But when we have positive acceleration, that's where we're looking at the slope of the lines again. So the only slope that has a positive, the only slope of the velocity function that has a positive value is between the 3 and 5 seconds or units of time that we have on the graph. Where does it have a negative acceleration? So we have two line segments that have negative slopes between 1 and 2 and between 2 and 3. So that's where we have negative acceleration. When is the acceleration undefined? Okay, undefined is going back to what we talked about when something is not going to be differentiable. So since the acceleration is the derivative of the velocity, anywhere I have a corner in this case is where I'm going to be looking at something not being differentiable. So the acceleration would be undefined at those points. So at 1, at 2, and at 3, those are where I have very distinct corners. So those are not going to be differentiable, meaning that the acceleration is not going to be defined at that point. State an interval of time when the particle has positive acceleration but is slowing down. This is where we're talking about the signs of the acceleration and velocity having the same value. So here, where the has positive acceleration but is slowing down. Positive acceleration, the slope of the velocity function being positive from 3 to 5 is where we have increasing acceleration, but because the negative or because the velocity function itself is negative over that time interval, over that same time interval, that's where we're looking at positive acceleration, but overall the speed is slowing down. The next one, here, state an interval when the acceleration is negative, but the particle is speeding up. Well, the only time it's going to speed up is when both is if acceleration is negative, but velocity has to be negative also. And there's only one segment on that line on the velocity function where the velocity is negative and the acceleration is negative, and that's between time 2 and 3. What is the particle's acceleration over the interval from 3 to 4? So the acceleration is the slope of the velocity function. So I'm really just looking at the slope of the line between time 3 and time 4. So we're just going to look at the slope here. And again, I keep saying time is in seconds, but I could be completely wrong on that. I'm just doing it to kind of give myself something. I don't know why I keep saying seconds and not minutes, but anyway. What is the particle's average acceleration over the entire 5-second time interval? So here, this is just a basic difference quotient, the average rate of change from one endpoint to the next. So we take the velocity at the end point and at the beginning point and take their, the difference quotient. And here, the average acceleration is going to be -1 unit per time squared. Unit of length per time squared. 28, over what time interval is the particle's velocity decreasing at a rate of 5 feet per, so here, maybe this is why overall I keep thinking feet per, or something in seconds, because here they're giving me some kind of units now. 5 feet per second. So between 1 and 2, that's where we're going to have essentially a slope of 5 feet. Over what time interval is the particle's velocity decreasing? Yes, 5 feet for every second. Yeah, so we're looking at things moving downward. Yeah, between time 1 and time 2. Between 1 and 2 seconds. So I understand that, guys, I get it. That was a lot of information, and I may have spoken quickly. I don't know. We're already at 41 minutes, but that was a lot of information, but it's very useful information. It's going to be something you're going to see a lot of in this course: position, velocity, and acceleration. So here, example 6, complete the table. Here, I want you to go ahead and try and fill in the table on your own first, and then hit play to see what I have. So hopefully you've filled in your table, and so here I have the things kind of filled in to help us understand what they're looking at. So when the acceleration is greater than 0, that means we have a positive slope. Acceleration is less than 0, we have a negative slope for the velocity. And when the acceleration is 0, then the velocity has a horizontal line. If the velocity is greater than 0, it's above the x-axis, less than 0, below the x-axis, and if the velocity is equal to 0, it's at the x-axis. So when velocity and acceleration both are greater than 0, that means that we're going to be speeding up. Same thing if they are both negative, we're going to be speeding up. It's wherever they're going to have opposite signs, where one is increasing and one is decreasing, that the particle is going to be slowing down. Okay? So here, if the acceleration is 0, regardless of the direction, that we're going to have a constant velocity. Now, if the velocity is 0 and we're slowing down, or the acceleration is positive, that means we've stopped accelerating, right or up. If the acceleration is negative but the velocity is 0, that means we've stopped accelerating, right or down, or left or down. And if velocity and acceleration are both at 0, it means the particle has no movement. Here, these are just vocabulary terms as far as things that we're going to be talking about: the displacement, average velocities, velocity at a specific time, speed, the absolute value of velocity, overall distance traveled, how you identify when directions change. And you all have this in your notes. You can read it at your leisure. And now I think we're nearly getting to the end. I think we have a couple more examples here. Now we have a model rocket that's launched vertically upward from the ground with an initial velocity of 114 feet per second. And the position of the rocket is modeled by the given function. So keep in mind that the derivative is the velocity function is the derivative of the position function. So it says find the velocity and the speed of the rocket at 5 seconds. Well, if I'm talking about anything in terms of velocity, I want to know what is the velocity function. So in this case, the derivative of the speed or the position function is going to be negative 32t plus 114. And in this case, we're looking at it in terms of 5 seconds. So I plug in the 5 for the time and just go to my calculator, probably really, to figure out this value, and we get negative 46 feet per second. So probably it's coming down at that time. You shot it into the air and it's coming down probably at that point. Is the rocket speeding up or is it slowing down? So here we need to know what is the, acceleration of the function. So the acceleration, the derivative of the velocity function, is going to be negative 32 feet per second squared. So at time 5, at 5 seconds, the rocket is going to be speeding up because the velocity and the acceleration at time is equal to 5 seconds are both equal, or are both negative values. So there's definitely going to be, because, and I had a typo there, they have the same signs, not opposite signs. That indicates that there's going to be, that the object is speeding up at that point. The maximum height, this is very similar, going back to what we saw with the Neil Armstrong on the moon question. I want you, at this point, you should be able to pause the video and work out except part C and part D on your own, and I encourage you strongly to do so. So presuming that you've paused the video and worked everything out, the maximum height, again, is going to be determined when the velocity is going to be equal to 0. So I take the velocity function and set it equal to 0, and I want to solve for time here in this case. So time is going to be equal to, when the velocity is 0, we get about 3.5 seconds. And I kept the entire number on the calculator because I didn't round it after 3 because it was a small enough value. But we're looking for the actual height. So the height at that point, that's when the velocity is 0, that's when the velocity is 0, so at just over 3.5 seconds, that's when we hit our maximum height. So I'm going to plug that function into our position function, and again, kind of go to the calculator, and that's going to give me overall a value of about 206 feet in the air. What is the speed when it hits the ground? So if I want to know the speed when it hits the ground, I have to know the time that it hits the ground. So I'm going to take the position function and solve it for time. And of course, I should get 0 for one time because you started at time of 0. Sorry, my phone keeps going off. But the rocket is going to hit the ground at about 7 1/8 seconds, 7.125 seconds. So if I want to know the speed, I'm going to take that and I'm going to plug it into the velocity function. But here I take the absolute value of the number, because if I plug that in, I'm going to get a smaller number than what I think it's going to be. But here we're going to be we're going to have a speed of 114 feet per second when the rocket hits the ground. And again, you don't really have to have a strong grasp of the calculus stuff, because all of those kinds of questions you've seen in lots of different classes before calculus. Okay, so now the last thing that we're going to be looking at here is something called the effect of a 1-unit change. And this is basically something that you can use as an estimate to give you an approximation of what you should be getting in regards to a situation. And to be honest, we're really not going to see a lot of this particular concept. Here, the final example that we're going to be looking at, for speeds between 30 miles an hour and 75 miles an hour, the stopping distance after brakes are applied for a vehicle is modeled by the given function, where F is in feet per second, the distance that it takes for you to stop over some given amount of time. For a vehicle traveling at 65 miles an hour, we want to estimate the change in stopping distance. Now, the estimate is going to be taking the position function that was given to us and actually plugging in 65 miles an hour and 66 miles an hour, and then taking the difference of them. So at 65 miles an hour, the stopping distance is going to be about 283 feet. At 66 miles an hour, we would do the same process, and we would say that that's going to be about 290 feet, so 290.4. So we take the difference of those, and that's going to be the approximate. Okay, that's the approximate increase in stopping distance that it takes for whatever this vehicle is modeled after to stop if you increase your speed by even 1 mile per hour. So it's going to give you need just under 8 feet, and that's your approximate. Okay. Well, the actual stopping distance is going to be found by taking the derivative of the position function. So the derivative of the function that was given to us, and I had a typo here. The position, or blah, blah, blah. The derivative of the function that we started with is going to be 1.1 plus, not minus, and that was my typo, plus 0.1 seconds. So now we have that function, and this is where I'm going to plug in my time. Okay, so here, taking my derivative in this case, we would say, okay, well, at 65 feet, we get about 7.6 feet for every mile per hour increase over 65. So the actual increase in stopping distance is 7.6 feet for every mile per hour you're traveling above 65 miles per hour. And the estimate that we got by just doing direct substitution was 7.65. So, like I said, it's a way of giving you an estimate. It's an approximation. You didn't actually have to do any calculus to get that estimate, but the calculus doing the derivative of the function that was given to you gives you the exact value versus the approximate value. Sometimes that's good enough, getting the approximate value. Sometimes you need the exact value, but and that is going to wrap up this lesson. Again, it's just a lot of information. If you need to, go back over and look at those, particularly all those 20 some odd questions that we had, talking about how we interpret the position, velocity, and acceleration, where we had that velocity graph, and we had all those questions based on it. That's very important information. But until then, guys, thank you so much for just being the awesome kids that you are, being the awesome people that you are, and I look forward to seeing you in class soon. Until then, guys, be good, be safe, and take care.